Well, we are going to be just spending a little bit of time here today looking at some AP Physics C electricity and magnetism questions. Let's see if I can find this for you. Boom. Well, there's the solutions to it. Boom. That's what we're looking at today. Problem 2. So if you want this actual problem, it's right there. If you want the solutions, we're going to be doing them. But if you also want the solutions just for the future, maybe you can't stick around for the full thing, the solutions are there. I'm going to show you how to get through all the solutions and how to set this up. It's pink on pink day. That means it's Wednesday. And we're going to get started here in just a second. I think that's all we're going to get. If anytime you got a question with this, just bounce something in. Let me know. Hopefully I'll see it and whatnot. You know, sometimes I just get so engrossed in the problem itself. But I'll be sure to clear everything up at the end of it if we get anything there. Okay? So let's get started. So like I said, what we're looking at here is the AP Physics C Electricity and Magnetism 2007 free response question. Specifically, we're looking at question 2 here. And in this question, we actually have kind of weird setup you normally wouldn't see in the real world, but we can look at it from a physics perspective. What we have here is on the inside in this blue sphere, we have a solid non-conducting sphere. So it's non-conducting, which means that the charges can be stored throughout it. It's solid, and it has some radius A, as shown in the picture, with a charge plus Q uniformly distributed throughout its volume. It's volume there, okay? And then it's concentric, meaning that there's one just on top of it containing that sphere, with a non-conducting spherical shell of inner radius 2a and outer radius 3a. So then you've got this shell, which that's the inside of the shell, and this is the outside of the shell right there. And that has a charge minus Q uniformly distributed throughout the volume of it. And that's another important thing there, the volume of it. Express all terms or all answers in terms of the given quantities. So those are A's and Q's and X and Y's if we use them for anything. And fundamental constants as always. So part A here is a 4-part Gauss's law. It's Gauss's law, Gauss's law, Gauss's law, Gauss's law. So let's take a look at applying Gauss's law to electric fields, because his equation looks weird to begin with, but as we start diving into it, we'll see it's really not going to be that bad. So if we want to do this for within the solid sphere, and that's the blue region in here, well, we'll first start with Gauss's law. So Gauss's law states that the closed integral of an electric field dotted through an area, and this just equals the flux, what flux is passing through this area, is equal to the charge enclosed inside that area divided by epsilon naught, the permittivity of free space. And basically what we're trying to do is we are trying to set up some sort of Gaussian surface so that if we had some Gaussian surface, you know, some sphere tucked within the sphere of charge, how much charge would that hold? Because then at this point we could designate the electric field there. So looking at this strange looking integral symbol, that closed integral, is really the closed integral around the area of the Gaussian surface that we created. And since we're looking at spheres here, a really great Gaussian surface to use is the sphere itself. That way, all the electric flux coming out of those charged spheres is going to be passing perpendicular to the surface of the Gaussian sphere we're setting up. So because that flux is passing perpendicular, we don't have to worry about this being a dot product, and we don't actually have to worry about this integral either. We know what the surface area of a sphere is. The surface area of a sphere is just 4 pi r squared. So we can just quickly say in this equation that we get the electric field times, and then the integral of that area is just 4 pi, and then however far out we went in this radius. Maybe we went a small little bit to there, maybe went a bigger bit, maybe went a bigger bit. But either way, that's just some value r. So this is just 4 pi r squared as the radius of our Gaussian sphere, and this once again equals the charge enclosed over epsilon naught. Now the thing that gets a little bit tricky about these questions, especially with Gauss's law, and something we need to remember, is that charge enclosed is unknown to us at the moment. We know that this inner blue sphere has a charge positive q uniformly distributed, but we don't know how much charge is going to be at some arbitrary radius, because that radius that we set, it's just within that inner sphere. So what we can do here is we can say, well, this charge enclosed here is simply equal to a charge density, which is uniform, it's a constant, times some amount of volume that we're enclosing. So how much volume are we enclosing in that sphere, and what is that charge density? Well, the charge density can be given to us as just the total charge inside that inner sphere, which that was plus q. Okay, so that's the total charge divided by the total volume of the blue sphere. So that is 4/3 pi, and then the radius of that inner sphere they gave to us in terms of a. So we can say that it's 4/3 pi a cubed. That's the entire radius of that inner sphere. So what we've got is the total charge divided by total area. That's a density, just like you could say mass divided by volume. We're just saying charge divided by volume. And then we need to multiply that by the volume that we are actually out at for our Gaussian surface. And in our case here, that's going to be 4/3 pi and then some distance r cubed. Luckily, a lot of stuff ends up dividing out. The 4/3 go away, the pi's go away, and we see that our charge enclosed is just going to be equal to the total charge plus q, that was the blue circle on the inside, that sphere, times r cubed over a cubed. So that's what we see there. So we can take this value and we can put it in for our charge enclosed, meaning that we now have a pretty nice equation to play with. We can now say that the electric field times the Gaussian surface area, 4 pi r squared, is equal to q r cubed over a cubed over epsilon naught. And then just cleaning up this math here, we end up seeing that 2 of these r's are going to cancel out, they're going to divide out. And then we're just going to divide each side by the 4 pi, which results in us getting an answer of that the electric field is just equal to, well, we note here we've got a 1/4 pi epsilon naught. So we could write that as 1/4 pi epsilon naught, or we just say it's k, the Coulomb constant. And then we're just going to say this is k q r, and then over a cubed. Remember that epsilon naught went into the k. So boom, right there, we've got an answer for part 1. It was a little bit of algebra in order to do that, and the big piece here was recognizing what the charge enclosed was as this. But the calculus wasn't really a headache for us. We just said, look, we use a sphere, and that sphere becomes 4 pi r squared. So just like that, we've solved for the electric field within that initial solid sphere, and now we need to do this 3 more times for different radii. Well, if you want to do it between the solid sphere and the spherical shell, so what's your electric field at any point within this purple region? That's not bad to do. We still use Gauss's law. The electric field dotted dA equals the charge enclosed over epsilon naught. If you take a second to think about what your Gaussian surface is going to be, well, you're still enclosing a sphere. So your Gaussian surface should be a sphere, which means that this dA bit right there, when we integrate it, is just going to be the same 4 pi r squared as before. So we get the electric field times 4 pi r squared, it's like we're doing the last problem again, equals the charge enclosed over epsilon naught. And in this case, we know the charge enclosed. We've enclosed exactly positive Q. So we can just say that this is positive Q over epsilon naught. And just like that, we can clean this up and solve this out. We can just say that the electric field equals Q over, well, if we divide each side by the 4 pi r squared, we're going to get 1 over 4 pi epsilon naught. So I can call this K here, KQ, and then we're going to get an r squared in the denominator. And hopefully you realize that that equation right there is just the electric field of a point charge somewhere in space. So we can think about a sphere of charge as really just a point charge centered at the middle of that sphere. So a kind of a neat effect we see from that, KQ over r squared. Now, this third one here is actually going to be a little bit more challenging. So let's skip it just for a moment and then go to the fourth one real quick. So if we're outside the sphere at a radius greater than 3a. So what's our electric field going to be if we're way out here somewhere? Okay. Well, let's just think about this for a second. We know it's going to be the Gauss's law, so the integral of the E field over some surface area. And we know we're going to pick a sphere again because we still have spheres here. But what's the charge enclosed? The charge enclosed inside of some large Gaussian sphere that we could create is plus Q and minus Q. So because we're enclosing a positive value Q and then a negative value of Q, we actually are not enclosing any charge here. So what we can just quickly say here is we can say that the charge enclosed here is just that positive Q from the inner shell, or that inner sphere, minus or plus the negative outer shell, which equals 0. Then if we used Gauss's law, this is what we're going to have. The integral of the E field through some area is equal to 0 over epsilon naught. And that yields that the electric field equals 0. And that's it. So we don't even actually have to do anything there. We just know that it's 0. That's a really easy one for us. Now, like I said, this one previously, within that outer shell somewhere, so what is it when you're in the red region? This one's a little tricky. This one's a little tricky here. And the reason why it's tricky is trying to figure out how much charge you're enclosing. That's the tricky part here. Because we know we're still going to use Gauss's law. And you see me writing this over and over again because that is what the College Board and what the graders want to see. They want to see that you are using Gauss's law and that you are applying it appropriately. So we write it again. And once again, we know that this integral of the dA is going to give me a 4 pi r squared. So if we write that again, we get that the E field times 4 pi r squared equals this charge enclosed divided by epsilon naught. Now this charge enclosed, like I said just moments ago, this is where the headaches come in. Because as we saw in problem 4, we can add these charges up and the positive and negatives are going to cancel out. Well, this means when we start looking at the charge inside some red region here, the charge that we're going to have enclosed, well, it's going to equal that initial positive Q, because we've got that positive Q right here on the inner sphere. But we also have to subtract some amount of charge that we're putting in this outer donut. Now, if you wanted to find the volume of an outer donut, what you have to do is you have to take the top side of the donut, the outer edge, and subtract it from the inner edge. Because what we're doing here is to find this ring of charge, this outer ring here, this red outer ring. What we're doing is we're saying, look, I'm out at this point, but I need to remove everything within it in terms of volume. So to find the volume of a ring of charge, we need to remove the outer shell and the inner shell from that. And the way we do this is we subtract this outer edge minus the inner edge. Okay? Now, before we even do that, we don't know the charge density of that outer ring. All we know is that it has a charge minus Q uniformly distributed. So this is getting more math that we have to do. And if you're running out of time on this question, maybe it took you a while to do parts 1, 2, and 4 here, skip this, come back later. But we're going to do it here so you can see everything, okay? Well, let's first just find what is the charge density of that outer region. Well, the charge density of that outer region is just given to us by the total charge in that outer region minus Q, okay? Or we could just call it Q for now because we know we're going to subtract it anyways. And then the volume of that outer region. Now that outer region is a big sphere with a smaller sphere taken out of it. And the big sphere that we have is the 4/3 pi, and then this is 3a cubed. Notice I've put the 3a in parentheses because it's 3 times that radius a, and we're cubing that. So that's the big sphere that we have. And now we need to pluck out of the center of it a smaller sphere. So that's going to be minus the 4/3 pi 2a, that's the inner sphere that we're popping out, squared. So that is the charge density. And if we clean this up, these numbers are not going to be pretty, but if we clean this up, that's 3 cubed is 9, 9 and 4 is 36, 2 cubed is 4, 4 and 4 is 16, divided by 3 on each of them. We're going to get, there we go. We're going to get Q over, and then let's keep the 4/3 pi. And then if I've got, well, this here we'll say is 9, and then we'll say this is, oh, whoops, this is a cubed. How did I mess that up? That's a cubed. So that's not 9, that's 27, excuse me, and that's 8. 27 minus 8 gives me 19. So I'm going to get 19a cubed left over. Whoa. That's what happens whenever you mess up your simple math. So that's the density of that outer red sphere. So now if we want to find the charge enclosed in that outer red sphere, then we need to take a look at what volume we are containing. So that charge enclosed is just equal to a density times some volume out at that radius. And the way we can think about this is we have our charge density right here. We'll put that in just momentarily. But, so I'm leaving some space for our density right here. But our volume that we're enclosing is very similar to what we've done just down here. We're out at some radius to make a shell, and then we're subtracting some inner radius from that. So what we can do for that outer radius is we can say it's 4/3 pi and then some radius away, I don't know what it is, but we're some radius away between 2r and r cubed minus that inner shell that we're taking out of it. We're punching a hole in the donut, and that's 4/3 pi to a quantity cubed. Okay, and then let's just put back what our charge density was. It was q over 4/3 pi 19a cubed. Okay, so what do we get here? Let's run down some math. I can pull the 4/3 pi out of all of this, and then 2 cubed is going to be 8. So what I can say is this is going to give me now some charge q over 4/3 pi 19a cubed times the quantity 4/3 pi of r cubed minus 8a cubed. And then we see that our 4/3 pi go away. That's great. And we could say that the charge enclosed here is equal to q times r cubed minus 8a cubed over 19a cubed. Okay, so that is our charge enclosed in the outer red sphere. Okay, so that's the red ring. Spelling right, red rig. That's the red ring charge. So what we needed to do, though, because that was just the red ring, is we need to subtract that from the actual charge from the inside as well. So our charge enclosed here is actually going to become, for the charge enclosed of the entire Gaussian surface, is going to become Q minus the charge that was enclosed by that red ring. And that charge enclosed by the red ring there was, as we had before, Q times r cubed minus 8a cubed over 19a cubed. And at this point, we've got some math to solve here. Well, how would we do this math? Well, we can do this. And like I said before, if you're getting stuck at something like this, just jump forward. Skip the part, get some easy points. But we're doing everything. What we can recognize is we've got 8a cubes and a cubes in the denominator. So we're going to rewrite this as q minus qr cubed over 19a cubed. And then I'm splitting that subtraction, so the minus of a negative is going to be a positive. So this is going to be plus 8, and then it's going to be a cubed over 19a cubed. Oops, and I forgot a q right here. I forgot to distribute my q into both of these. I remembered it there, almost forgot it there. And what we see is that these a cubes divide out. So this is what I'm going to have in the end. I'm going to have this giant term right here. Honestly, if I was taking the AP test, I'd just leave it like that because I don't want to do any more math from here. If you really got excited about doing some math from here, you still got 2 points to go get. So let's just do it. Let's just work it all out. Remember, this is just to get the charge enclosed inside this setup. What we end up getting here is that This is 19 over 19 q's. 19 plus 8 gives me 27 over 19 q's at some point. And since they all have q's, I'm going to pull the q's out, and they all have 19s. I'm going to pull the 19 out. So I'm going to get q over 19, because this is really like 19 over 19 q's, right? So I pull the q's out. I pull all the 19s that we have out. And then what I can say is that since the 19 here plus the 8 here, that gives me a value of 27 minus, and then since I already pulled these out, I'm just left with the r cubed over a cubed. Okay? And that's equal to our actual charge enclosed inside of our Gaussian sphere here. Which means that I need to take this and I need to go all the way back to right here and drop it in. Which is so much work just to get to that point. Okay? But that is what we have to do. So we come all the way back to the beginning of our problem. And we'll just clear some space here. Clear some space. And now we can say that the electric field times 4 pi r squared equals q over 19 times 27 minus r cubed over a cubed. And then we need to divide this by the 4 pi r squared, which is going to give us, at the very end of all of this, that the electric field equals q over, well, 4 times 19. 19 and 19 is 38. 38 times 2 is 76. Pi r squared times, well, there's an epsilon not here. Whoops, epsilon not. Times the quantity 27 minus r cubed over a cubed. And this right here, that is our answer. That was so annoying. That was so much work for 4 points. And honestly, we would have gotten some points just for doing this. Just for writing this right here, this would have gotten us a point. So that's why we always write Gauss's law out. We got a point just by doing that. And there's only 4 points in this problem, so I don't want to do all that work. Okay? So get that point at least, and if you're struggling with the math and whatnot, just move on. Whew. Still going. Still going strong. What are the electric potentials at the outer surface of the spherical shell at r equals 3a? Explain your reasoning. Well, this is an electric potential. And another way we can say electric potential is a voltage V. And what we can remember are these two things. We know that an electric field is equal to the opposite of the derivative with respect to the position of the voltage. And what that means is that the integral of that electric field with respect to some position equals the voltage. Okay? Now, we're looking on that outer surface of that shell, 3a. So the real question is, well, what's our electric field out there at that position? Well, out there and beyond that, the electric field's 0, because the charges on the inside and outside have canceled. So because the electric field is 0, the voltage has to equal 0 here. And that's it. 0 volts. Boom. You're a winner. Okay? So we can just quickly do it like that. If you wanted to, whoops, there's a negative there. If you wanted to prove that with your boundary conditions and then show the math, your boundary conditions here are going from some infinity distance away to just 3a. Because remember, we always think about potential being 0 way, way, way out at infinity, and then we bring it in from there. So we say that we just get 0 here. So that was nice. That was a nice little problem. And that right there, that actually got you 3 points. So just doing that right there, this was 3 points, and all of this in part 3 was only worth 4 points. So don't waste your time doing all that math in that third part when you can get nearly as many points for doing so much less work. Okay? Remember, they're just trying to see if you know what you're doing, and you're just trying to get points where you can. For the last one, part C here, we are looking to derive an expression for the electric potential difference. So what is the potential from one point to the next? Those points are Vx and Vy, which are the points X's and Y in the figure. And just to give us an idea of what we're looking at, we can come up here and look at our figure again. So we're looking at from points X, that's our final position, to point Y, that's our initial position. So we're actually going Y to X in this case, which means that our initial distance away where we're starting is at 2a, and then we are ending at a radius of 1a. So that's an important thing to keep in mind when we do that. We're starting from far out and we're coming back in. Well, just like we said right up here, we know that the potential difference is just the opposite of, the electric field is just the opposite of the potential difference, or we can run an integral here to get our values. So a quick way we can do this, there's two real ways we can do it, is we could take the integral, or the minus integral of our electric field from the initial point, which is the outside 2a, to the inner point where we're ending a. And we would just run that of the electric field as a function of the radius, and that would equal a difference in voltage for us from the y to vx, okay? Because this is technically a final minus an initial here. We know an expression for the electric field from a to 2a. That's actually just saying this is the negative integral from our bounds of kq over r squared. And since k and q here are constants with respect to r, so that's a dr, this integral just quickly becomes the integral of 1 or dr over r squared. So we can say this is just kq, well, minus because the negative, from 2a to a of dr over r squared. When you take the integral of dr over r squared, that's just a regular polynomial, so we can bring this r squared up to the numerator. That's like r to the negative 2, and the integral to r negative 2 is going to give us negative 1 over r from our bounds of 2a to a, and then we're going to get a minus kq outside of that. If we take our bounds and we do our upper minus the lower, both of these values going in for r, we're going to get minus kq, and then times the quantity minus 1 over a, and then minus positive, because we subtract, but then there's that negative here. And this is going to be 1 over 2a. And when we do that, we could just write this out as maybe it's going to be easier to do this. We can take the negative sign and drop it through to each of them. So this is positive now, and this is negative. 1 over a minus 1 over 2a is just going to be 1 over 2a. So we're going to get kq times 1 over 2a, or just over 2a. And that's going to be our voltage difference from x to y. So that's one way we can do that there. Another way we could have done it is we could have just said, hey, what is the voltage at x? What is the voltage at y? And we know what those voltages can be because we have an expression for them that we found before. It's just the point charge expression. So we could have just said here that at Vx, the inner radius, it's just going to be kq over a, and Vy is just going to equal KQ over 2A, and Vx minus Vy is just going to be KQ over 2A, which is what we found anyways. So you could do that problem in two different ways. You could either use values you knew from before and just take the easy way out, or you could actually run that integral and solve it. It's really up to you on that one. So anyway you cut it, you're going to get the answer. We found in this problem that the long part was within that spherical shell from 2A to 3A. You know, this pesky region here, what is that electric field? And it's simply because they don't give you the charge density here, and you have to find it, and you have to find volumes. So depending on how your problem's set up, you may just want to recognize that, hey, that's my time sink. I'm going to dodge it for now. I'm going to come back to it if I have some free time. Because, you know, even if you only got 1 point here for setting up the Gauss's law, that's still 1 point. And if you got everything else here, which was much, much easier, then you're sitting pretty at something like 11 out of 15 or 12 out of 15 points. And you should feel really, really good about that kind of score on a free response question. Okay? So once again, this was the AP Physics C Electricity and Magnetism free response question from 2007. It's question number 2. We're looking at spherical systems of charges concentrically set up and looking for the electric fields using Gauss's law via them. So I hope that helped you out. Check out the other videos. We've got a bunch of arcs of charge. We've got some other Gauss's law. And in the coming days, we'll be putting up some RC circuits, RL circuits, induction, everything we need for this test. So check it out and take it easy, because this problem is finished. And yes, it's a mighty fine comb over. It's the finest in the land.